Okay, welcome everyone to the UCSD CSE Database Seminar. Today we have an exciting speaker, Dr. Tianqi Chen. He is a faculty member at Carnegie Mellon University and co-founder of OctoML, startup in the machine learning system space. Tianqi doesn't need much introduction in the data science and machine learning systems world. Many of his previous systems that he built as part of his graduate research and subsequently working on now as well have seen mass adoption, XGBoost, TVM, MXNet, and so on. So he is going to tell us about what he thinks of how to build learning systems. So welcome, Tianqi, and take it away.
Yeah, thanks for the introduction. So so everyone, today I'm going to tell you a bit about basically some of my past work on learning systems. And to get started, one of the things that we have witnessed is, machine learning itself have becoming so successful and ubiquitous in a lot of the areas we are looking at, including, but on the other hand, it's usually useful to think about, why is machine learning applications so successful nowadays? I think there are a few elements in here. So for the first element is machine learning models. And as we know that machine learning model research starts very early, like as early as 1960s, a lot of the algorithms we are interested in, like support vector machine, ConvNet, LSTM, and gradient boost machine are invented before the year 2000. Around year 2000, one thing that happens is that the boom of Web 2.0 and a lot of content being created through the internet that creates a huge amount of resources for machine learning researcher to basically fuel the machine learning algorithms. And around in 2006, we started to see competitions and data sets coming that are normally bigger than a normal toy data set we see. For example, the Netflix challenge started to open a new area of recommender system, large-scale recommender system. ImageNet is certainly one of the very important milestone that allows us to open the paths of deep learning areas. Today, the data comes in a more diverse form from phones, mobile devices, and other things. And data is certainly one of the important axes to that enables the successful machine learning as well. The huge amount of data set actually creates a big challenge for supporting and sustaining the machine learning models, so which put compute on the spot. Around year 2006, the arrival of public cloud really makes it easy for us to be able to scale machine learning onto multiple devices easily. The machine learning researchers started to adopt GPUs around the year 2009. And since then, GPU still is the powerhouse of modern day machine learning research. Today, we start to see a trend of more hardware specialization, where we start to build specialized hardware like Google's TPU and a lot of other specialized hardwares for further accelerating machine learning research. As you can see, that machine learning success is not really only due to one element. There are three elements that really comes together that enables the success of the golden age of machine learning, both in terms of machine learning algorithm research, the data that we have, and the compute that we can leverage. However, there's still one missing ingredient in here. So to motivate that, actually, 10 years ago, I was an undergrad researcher at Jiao University, and at that time I was working on doing research on an area of deep learning, actually, and at that time I have to spend 10 months to handcraft CUDA code in order to get my model running on GTX 2080 GPU by then. Today, I only have to write a few lines Python code to do that. So that huge amount of improvement is thanks to the arrival of machine learning system research. Around year 2010, we started to see quite a lot of interesting machine learning systems emerging, including GraphLab for general purpose graph processing, Apache Spark for general purpose data processing, Scikit-learn for general purpose machine learning, Caffe, the first generation of deep learning system, XGBoost, MXNet, TensorFlow, and PyTorch are this generation of machine learning, deep learning system. These machine learning systems really allows researchers to write a few lines of code to express the high-level intent, while handles the offloading to each kind of like a diverse kind of hardware and do training on diverse kind of data set. So today I'm going to quickly tell you a bit about some of the lessons we learned by working on these past learning systems. In particular, I'm going to use 3 examples to tell you about some of the lessons learned: XGBoost, MXNet, and the TVM. So I'll start with XGBoost. And there are a few themes that I want to cover actually through these learning systems. So first thing I want to cover is the accessibility point of view. So XGBoost is a gradient tree boosting system that allows us to effectively learn gradient tree ensembles for doing quick prediction. And it has, since it's been released, it's become one of the de facto tools for data scientists. It has been used by more than half of Kaggle weighting solutions, used in Large Hadron Collider prediction to predict Higgs boson related events, and being deployed in major companies. One of the important perspectives in XGBoost though is, there are a few technical highlights, but I want to talk about one important perspective is ability to automatically handle missing values. So as we know that in a lot of cases, when data scientists trying to process their data, there's a typical one step called data cleaning, right? So because in a lot of cases, when you're trying to collect data set, there are always values that are corrupted or missing due to either the user is refused to put in certain information got hide, or just the data is missing due to imperfection in the collection process. So traditionally, data scientists will need to make use of data cleaning techniques like imputing median values or mean values or other ways to basically handle the missing value before feeding into machine learning models. This creates quite a bit of barrier for beginners, since beginners will need to learn about how do you process clean up the data before you start to feed them into averages. So one of the interesting features that XGBoost brings in is the ability to model the missing value behavior. In this case, in order to learn a decision tree that handles missing values, in this case question mark, what XGBoost is doing is that it will learn to add what we call default direction, which is in the red, when the value is missing. So this is an enhanced version of decision tree that not only tells you decision rules on whether a single variable is smaller or bigger than a single value, but also it also have a condition on if the value is missing, which direction we should go to. More importantly, this missing value direction, or what we call default direction, is learned jointly with the other decision tree conditions. So that the idea is that we want to be able to learn the best missing value direction from the data for each of the decision tree that we're having. And if you think carefully, you can find that this approach actually corresponds to the learning on which value you want to impute in each of a tree, because if you really impute a value there, it will imply a missing direction in your final decision tree. So while this is like a quite minor feature when we build the system and when we write about a paper, it's just get a small section in the paper. This is actually one of the major reasons why a lot of data scientists adopt XGBoost as their de facto tool. And it also teaches us later, like the importance of making machine learning system really accessible to those who might otherwise wouldn't be able to make use of this. So after touching about accessibility point of view, the second perspective I'm going to talk about is scalability. This is of course a lot of learning systems. When you talk about learning system research, this is one of the quite frequently talked about topic of learning systems. In particular, I want to tell you a bit about how do we scale up deep learning through building systems in MXNet. MXNet is one of the first scalable deep learning system before TensorFlow, and it's being adopted by Amazon. And there are a few technical highlights, but today I'm going to tell you a bit about how can we train deep neural networks with less memory. So the problem here is that as we start to build machine learning research, researchers like to learn bigger and bigger models, right? If you start to see the recent GPT-3 model, there are billions or tens of billions of parameters and layers and a lot of layers in the model. So, but however, in all cases, one of the problems we always face is we'll run out of GPU memory, and that's why it's one of the hopes is that we can just hope NVIDIA and other GPU vendors to build us GPUs that have bigger and bigger GPU memory. On the other hand, it's also interesting to ask, can we make better use of limited GPU memory there? So one of the common actions that we do for training deep neural networks is what we call backpropagation action. In this case, what you need to do is you do forward propagation, and then you do back propagation to get your gradient for each of the intermediate weight. The problem here is that in order to calculate the gradient in a backward pass, we do need to remember the intermediate value, because we will need them in the back propagation rule to calculate the gradient of the weight. So that makes the memory complexity of training unlayered neural network to be linear to the number of layers that we have in the neural network. So the question is, can we do a bit better than this linear case, right? The answer is actually yes. So the idea is that instead of checkpointing or remembering every stage of computation in a forward gradient, what we can do is we can only store some of the color nodes in here, and doing backward pass, because this uncolored node do not have the value, so we will need to recompute this small segment before we are able to do a mini back propagation to backprop back and get gradient of each of the layers. Similarly, we can do recomputation of other segments. So in this case, what we can find is the memory cost of this partial checkpointing action correspond to the memory cost of storing the intermediate computation in the forward pass, and the memory cost of doing this mini segment computation within each of the stage. So we have this nice formula that trade off these two, and if we pick the potential checkpointing strategy cleverly, we can find that we can get to a square root cost of the number of layers in terms of memory complexity, and you only have to pay one additional cost of forward pass, which is usually only 25% of the original cost of your end-to-end training. So by doing this, actually we can scale deep learning training to much deeper neural networks. So in this case, we show that by using a sublinear plan, actually we can train a 1028 ResNet on Titan X GPU, which is something that we wouldn't be able to do before. And if you don't use the sublinear memory trick, you will only be able to train, say, at most 200 layers on a single GPU. Okay, so after we briefly touch about XGBoost and MaxNet, if we summarize both XGBoost and MaxNet, what you can find is that both of them are systems that we try to build to enable better machine learning. On the other hand, there's the untold story here. So the untold story is that in order to build and optimize these systems, there's a lot of engineering effort that we need to put into that. And I personally spent a lot of effort in first 3 years of my PhD working on optimizing those systems. So the question we have now is, it is really time consuming to do this system level optimization. And given machine learning is so smart, can we actually use machine learning to optimize those systems instead? The answer is actually yes. So that's what we want to talk about. The third perspective, which is the intelligent learning system view. The idea is that not only want to build a system that enables machine learning, but we also want to build machine learning solutions that optimize those systems. And as a result, we can spend less amount of engineering effort on building those systems. And in particular, I want to talk about these themes of intelligent learning systems in the context of TVM. So TVM is what we call end-to-end deep learning compiler. The problem we're trying to solve is we want to be able to deploy deep learning programs onto different kind of hardware we're interested in, including CPU, GPU, and TPU accelerators. The problem nowadays, however, is that it's really tricky to do that in nowadays frameworks. So why is it tricky? So in existing frameworks, usually what you will do is you will represent those high-level computations in the framework like TensorFlow and PyTorch in what we call high-level data flow graph, where each of the colored nodes in the data flow graph correspond to a primitive tensor operation, such as high-dimensional convolution or matrix multiplication. The problem, though, is that in order to offload those colored nodes onto the low-level device, we will need to rely on low-level implementations of those colored nodes. For example, in the case of NVIDIA GPU, there's a library called CODN that implements some of those operations. So the limitation of the existing approach is that for each of the colored nodes in the high-level computation graph, you have to see a corresponding low-level implementation in CODN. However, because of machine learning is a fast evolving field and people want to do interesting optimizations onto those computational graphs. For example, one of the optimization that you might want to do is you want to sometimes fuse the operator together to this what we call blue node that gives you a potential benefit in terms of speed up. The problem, however, is that this blue node is no longer exists in the low-level library. In this case, CDN. So what do? A normal case is that you go and ask NVIDIA to add this blue node to the low-level library. However, it will take usually a month or even a year in certain cases to do so. Or you can just hire another person to add that library. And that's a common practice in this big company. The problem is that if you multiply that by the amount of hardware that we want to support, this is really an engineering intensive process. So the idea of learning-based learning systems that want to do better by replacing those human-based effort by machine learning-based program optimizer that automatically learns to generate low-level code that allows us to directly run on the low-level workloads and hardware platform. So specifically, for each of the column in the high-level computational graph, what we can do is we can represent the semantics of this each of computation using what we call tensor expression language that describes the high-level computation on how would you want to compute each element of a target tensor. For a given specification, we can define a search list of possible program optimizations that gives you a different variations of low-level programs. For example, to give a sense of what are the possible low-level programs there, for example, we could do things like generating vanilla code that implements the matrix multiplication in this case. Or we can, if you are optimized for CPU, you can do things like tile transformer loop a bit so that you can get better cache locality. Or if you want to map to certain accelerators, you might want to map part of your computation into domain-specific intrinsics that are provided by those accelerators. At a high level, what we want is to build optimization space of billions of possible optimization choices. And our question is how we can quickly explore that space to get you a good optimization choice. So to formalize it a bit, what we have is we have a specification, which is the E, and a search space of the tensor expression. Our goal is to be able to generate optimized configuration that we can then feed to the program generator. And that program generator will be able to allow you to send the program to a target hardware for measuring the cost. And our objective is to minimize the cost, to find the best configuration that minimizes the cost. So there are a few ways we can do it. For example, one way that we can do it is what we call black box optimization. So the idea is that you can just repeatedly try different configurations, run on a target hardware until you find a good one. The problem with this approach is that it's really expensive to try a lot of them because the search space can contain billions of potential choices. Alternatively, we can learn from database community where what we can do is we can try to build a cost model for a given program configuration and use it as a surrogate for us to pick the best configurations given the cost model. The problem with this approach is that because we want to target a lot of hardware backends, it's really hard to build a reliable and accurate cost model per hardware backend. So what we do instead is want to take a more statistical driven approach. The idea is that for a given high-level configuration, what we can do is we can try to lower this high-level configuration into a low-level abstract syntax tree and extract statistical features from that syntax tree and learn a statistical cost model to predict the cost for a given configuration. The advantage of this statistical approach versus the manual defined cost model is that we can learn to adapt to the particular kind of hardware we're interested in without having to do too much of modeling of that kind of hardware. Of course, another approach we can do is we can directly feed it into a neural network summarizer that in this case a tree GRU that summarizes the cost model and then summarizes the AST into a single embedding and then use that as the source for prediction. So to give a sense on how much benefit we can get by using this statistical based cost model driven method, here's an example of running TVM on a single layer, or using TVM to generate code on a single layer of ResNet on Titan X GPU. The x-axis is number of experimental trials. We send the generated code to the target hardware. And the y-axis is a relative speed up versus this baseline, which is a CUDA library. So if we apply a black box optimization, we can find that we can get decent performance after 800 trials. If we apply machine learning based method, we can find that we can get to better solutions within fewer number of iterations. The reason, intuition here is not really because the black box, the human is, the machine learning algorithm is smarter than human. It's really because in this case, ML algorithm is able to look into this particular workload and specialize into this particular layer. While when developers trying to write the convolution libraries, they try to build things that more or less generic, so that they can run more platforms easily, but not necessarily specializing to this particular workload. So besides this direct learning-based approach, another interesting chance that we can get is actually we can try to build what we call transfer learning-based method. In this case, assuming that historically we have already learned, cost model for collected data for different kind of workloads, like the first 10 layer of ResNet. I want to try to learn to optimize the 11th layer of ResNet. In this case, we don't really want to show all those historical data away, but instead want to be able to build a shared cost model to bootstrap the learning of the new task. In this case, it could be a different layer of the target neural network. And to give a sense, how much benefit we can get by using the transferable cost model. This is on this particular task, this is the original graph that we have. And by applying transfer learning by looking at previous 10 layer of ResNet, actually we can almost immediately get to the best performing computation kernel in here. Of course, the intuition, of course, it's not always true for all the cases. On average, we observe 3x to 10x speed up. So for different cases, it might still need a bit of iteration to pick up. But overall, we can find transfer learning usually gives you a good benefit of instead of doing things from scratch. So to summarize, in order to learn to deploy this bigger search space, we will be able to take benefit of a few characteristics of this target workload, and build a learning-based approach that allows us to iteratively explore the space while learning a better cost model through a statistical fashion. If you want to learn more about it, you can read about our newest paper. Okay, so now, yeah, go ahead.
I have a question. Sorry to interrupt.
Yeah.
The previous slide. This is very cool. So TVM is awesome. I actually covered that in my class, the CSE 291-234 that I'm teaching this quarter on machine learning systems, and the students liked reading about it too. It's a very comprehensive framework. One of the things that I was curious about is this ML for the compiler, right?
Yeah.
What is your take on the following, the thing about predictability and reliability of the performance of the model's output, right? So this is a question that, it's not my question. It's a question that Surajit asked at the MSR Faculty Summit for people working on learned query optimizers, right?
I see.
One of the issues was they're like, okay, the performance is not predictable. They cannot give SLAs. If a machine learning based query optimizer gives an output and then the query's runtime drastically differs from what a customer is used to, they may not like that sort of a jarring jump or drop in predictable runtimes. Now, of course, in the compiler context here, it's maybe less of an issue because the compiler is outputting the optimized code, and that is verifiable before you deploy it to the machine, right? The IoT device.
Exactly, yeah.
You can actually do this multiple times. But what is your take on how people can interpret these sorts of performance jumps or whatever? And have you tried to understand the robustness of this kind of machine learning based compiler, like kind of looked at variance across different kinds of architectures, where there are cases where it underperformed? What's your take on that?
Yeah, I think it's definitely an excellent question, right? So in a lot of cases, in the particular case of machine learning compiler, and in the case of deep learning, actually it's less of an issue because we can directly optimize the code and you can directly benchmark that, right? So you always have a fallback mechanism. I think that one of the important things for the ML-based solution is that you always need to think about a fallback mechanism, right? So in the worst case, there's something that you can fall back into so that it gives you the XLA if needed, but you can still get a lot of benefit in other cases, right? On the other hand, it's also, I think, on the other hand, a counter argument to that is, the human engineered solution are not necessarily predictable. In the sense that, as you will see in some of the later slides, most of the human engineered solutions are also specialized for the benchmarks and workloads that we care about, right? So in some sense, it's like humans are also statistically trying to fit into the benchmark. And there's also similar problems like overfitting to benchmarks while not being able to handle some of the surprising workloads. So in that case, it is not like a machine learning-based solution may not be a worse answer than a human-based solution, as long as you define your objective function carefully. Yeah.
Got it. So following up on that, second question I have is kind of debuggability for domain, like a system expert, right? Like the machine learning-based compiler, and if a compiler expert wants to look at it and figure out, okay, so maybe it's misbehaving, how do they try to sort that out? Do they need ML expertise themselves, right? Because now they have to understand the ML model and the featurization and then the implication, and it's also kind of requires ML expertise, right? Is that the...
That is the excellent question. And I think it's always an important theme, right? You don't want to, so besides the automation, another axis that we always want to consider is domain expert. In the sense that, there are domain experts who can write very fast code, and we want to really take benefit of them as opposed to directly let automation taking over, right? So I think this is a consistent theme that we see in TVM as well, in the sense that how can we combine domain expert knowledge together with the automation, so that if domain experts have more knowledges and opinions about what things should go, we should make sure we make use of that opinion. So through TVM, we are trying to do that by allowing for a domain expert to provide things like search template to describe potential search space that might be interesting. And there are other ongoing directions in the community that tries to address more of that. But I think it's an excellent point in the sense that, it's really hard to trust a fully automated system and say, this is fine, right? In a lot of cases, actually, this is more like a refinement process where, we learn from the domain expert, then those lessons goes into a system, making it more automated. But in the meantime, we still want to let the domain expert to have a way to interact with the system.
Got it. Okay, last question, and then I'll let you continue.
Yeah.
I really like the thing where you talked about the transfer learning across different devices, right? So the space of hardware accelerators for deep learning inference keeps on growing. There's like a new startup every other month or something. To plug into TVM, what would they need to provide? They would need to featureize the hardware specs in some manner that your model can reuse. But do they also need to provide extra training data, or what do they need to do?
So for now, what we do is, we allow the requirements mainly to be able to hook that into TVM's runtime. The idea is that, because we want to either it's by simulator or real execution environment, as long as we will be able to hook that into a TVM runtime, actually you don't necessarily have to featureize the hardware specific property, because learning-based algorithm will collect data and try to learn potential. Like for example, when we are trying to train for CPUs, we don't tell the algorithm, hey, the cache size is 5. It will learn a decision rule like, if the memory usage is bigger than L1 cache, that's a different behavior than otherwise, right? So these are the knowledges that machine learning algorithm is able to pick up. So we don't necessarily have to featureize that heavily, but one of the ideal cases is to be able to hook that into TVM's runtime and benchmarking. In order to do that, we do provide infrastructures. For example, right now, if you want to do benchmarking on mobile devices, TVM have what we call RPC protocol that directly allow you to do modeling and training in Python side, but still remotely send your program to the device, so to do quick benchmarking. So we contain infrastructure that allows us to easily basically provide hook your hardware backend into the system.
Sounds good. Great. Thanks. Let's proceed. Any other questions from the audience at this point? If not, we can continue. I mean, of course, feel free to raise your hand if you have a question, and I will ask Tianqi to pause.
Sounds good. Yeah.
Continue.
Yeah, so we have talked about AutoTVM. However, AutoTVM is a small but important part of a more bigger end-to-end system. And in this case, not only want to automate automation, but also want to build representations to be able to represent the potential high-level and low-level program optimizations that we might have. So I'm going to focus a bit about how do we define the low-level optimization and tensor optimization search space through a tensor expression. So to recap, for a given tensor expression, what we really care about is we want to define a search space of possible mappings from the tensor expression to valid hardware programs. And this is not a new idea. Actually, we are borrowing ideas from a lot of past good works, including Heli's image processing language and a few other, polyhedral compilation domain-specific language. However, the real question is how can we effectively define a search space that covers what programmers might do to optimize a program? For CPUs, actually, we can reuse a lot of the existing domain knowledges from prior works. For example, we can do things like, optimize for cache locality, vectorize the code a bit, and doing loop transformation so that we can get more local and continuous computation. Things become more interesting as we started looking into more different kind of hardware. For example, when you look into GPUs, one of the important things about GPUs, you want to be able to make use of the shared memory and allow different threads to cooperatively fetch data into a shared memory before you do computation. And things become mostly interesting when you start to look at TPU-like specialized accelerators. These accelerators are special both in terms of the computation primitives that they provide, for example, and the memory subsystem they have. In terms of computational primitives, traditionally when you try to build a program, normal programmers only have to write Scala programs, which means that you try to write, how do I compute each element of my target? And this is usually flexible. Things become more complicated when you start to want to use a vector unit in modern CPUs like AVX512 or R's Neo instruction. In this case, you have to represent your computation in the vector form so that you can make use of instructions that ask for floating point together or make a dot product of a floating point. And if you start to look at TPU accelerators, things become even more complicated, where most of those accelerators contains high-dimensional tensor instructions. For example, in the case of TPU, it contains the matrix application. And in the case of other accelerators, the primitive might be one-dimensional convolution or other memory loading instructions. And the challenge here is really how do we build a learning system that works with those emerging tensor instruction accelerators? Because for Scala and vector instructions, it's still easy to enumerate what are the possibilities, but the different choices, different shapes and sizes of tensor computation really makes it hard to enumerate all the possible tensor instructions beforehand. So in order to do that, what we call this challenge what we call tensorization as an analogy to the vectorization challenge in modern compiler. And in order to do that, what we do is, besides putting in a specification of the high-level tensor computation, we also want to provide a specification of the hardware instruction itself to describe what the capabilities the hardware have. In this case, we use the same expression language to describe the hardware interface. And in this case, this particular hardware instruction tells us that it can do an 8x8 matrix vector dot product. And our question is, through a process of tensorization, we want to be able to transform the high-level description to make use of the subregions that can be matched by the low-level hardware interface specification. And by doing that, we'll be able to make use of the low-level hardware accelerations when necessary. Right now, when doing tensorization, TVM still is a semi-automatic process where we ask developers to define a template that eventually be able to mix and match the low-level hardware tensor intrinsics. And there are also ongoing researches on how we can automate that process further. So to summarize, we can find that we want to be able to make use of the low-level transformation primitives from previous works for CPU and GPU optimization, but we also want to be able to build in new primitives for GPU optimization and enable TPU-like accelerators. The combination of this bigger search space allows us to make good use of the try to enumerate all the potential optimization that human programmer might write. And that's one of the secret sauce on why we might be able to outperform human programmers in generating those code. So to give you a sense on what we can get by putting everything together, here's the end-to-end benchmark on comparing TVM versus a few of other frameworks. In this case, both TensorFlow and MaxNet are backed by CUDN library from NVIDIA. If you directly run TVM, you can find that TVM can give you better performance. There are a few interesting highlights in here. So if you look at far left, on the Resonate 18 workload, we can get to about 25% to 40% speed up, which is pretty good, since this is like a heavily optimized standard benchmark. The most exciting thing though is if you look at far right, this is the deep Q-learning model. You can get more than 3x speed up on this particular workload. So this is a workload used by DeepMind to play Atari game. So what is the reason why can we get 3x speed up here? The reason is that most of the employees from NVIDIA are heavily overfitted to the standard benchmarks. In this case, ResNet is the benchmark that they are tasked to optimize for. While deep Q-learning is not necessarily a benchmark that everybody wants to optimize. But however, if we use machine learning based algorithm, we don't have this problem of overfitting to a certain benchmark, and we can always specialize to the particular workload we are interested in. And this is also one of the reasons why we believe this automated compilation solution is the future, because it can really enable us to work on more models that are not necessarily standard. And if you go and talk to a lot of customers in deploying machine learning models, usually their models are not that standard anyway. Another interesting thing is that we will be able to take the same solution and use that to build specialized solutions for specific hardware platforms. In this case, we can compare against TensorFlow Lite on ARM CPU and ARM compute library on ARM GPU, and still get better performance than each of them. And finally, another interesting thing is by using TVM, we'll be able to support emerging new hardware instructions. In this case, NVIDIA's Tensor Core. So this figure is a bit flipped. Since higher is better, we're comparing speed up against Tensor Core, against CUDN library. And what we can find is that actually by using TVM, we can get 1.4x speed up on this batch mainstream application workload, which is one of the core building block of transformer models like BERT. So again, it validates the importance on using TVM or using automated solution on those emerging machine learning workloads. So far I've told you a bit about what our support for CPUs, GPUs, and mobile GPUs. And of course, one of the interesting questions is how can we better support machine learning accelerators? And in this particular case, what we are trying to do is one of the problem of doing research on machine learning accelerator nowadays is that it's really hard to really find a hardware that supports your case, right? Because most of the machine learning accelerator nowadays are not open source, and you cannot even provide a low-level programming interface to those accelerators themselves. So what I did here is we built an open source version of deep learning accelerator called VTA that contains open source microarchitecture, a runtime instruction set, and a just-in-time compilation runtime that directly hook into TVM. So what you can do with VTA is that you can directly take FPGA and use bitstream to program VTA on the FPGA and directly compile TVM-based programs onto VTA to run on that. And if you don't have an FPGA, you can also directly run VTA simulator on your laptop. The advantage of VTA is that it gives you a open, transparent full stack, including the open source compiler, the open source driver, and open source hardware design. That allows us to do a lot of interesting research questions, like how do you co-design your hardware together with the high-level machine learning instructions? How do you build compilers for better hardware support? Or how we can do full stack co-design, including model, hardware, and compiler itself. One interesting thing that this end-to-end stack allows us to do is automatic hardware design space exploration. And in this case, what we can do is we can try to explore what are the block RAM size and the matrix and the size of the DRAM unit we put into VTA, and automatically find what is the best answer for a given workload. Okay, so we have talked about mostly the technical part. I want to use the last few minutes to talk about more the community part of the TVM. So TVM itself is a research project, and since we got started 3 years ago, we have incubated as a part of Apache project, which means that it has an independent governance model that allows competitors to collaborate. And so far, it have been used by a lot of industry partners, and they also have been used by a lot of research labs to do research in the area of machine learning compiler. And there are also groups in USSD that uses TVM to do machine learning compiler research, which is really great. One of the things that we always emphasize, they want to try to bring in new contributors to a project, and so that the latest machine learning system research can quickly get reflected into the production scenarios. So far, we have more than 450 contributors to the project, and every month there are more than 100 pull requests from more than 50 authors to the project. And because this is the open source community, it means that it's collectively owned by the contributors. And as contributors start to contribute more to the project, they will be automatically granted committer access to the project, where they will have a say on where the project is heading. So far I've talked a bit about our past work on TVM and algorithmics. That I want to spend a few minutes talking about what are the future potential elements for learning system. So far, when we talk about TVM, what we're trying to do is we want to be able to, for a given model and given hardware, we can define a space of programs, and then AutoTVM will give you an optimized program for that model and that hardware. One of the obvious questions is, can we expand that space by only thinking about by not specifying the space of models, programs, and hardware variants? And can we build a more full stack solution that automatically find the best combination of the three for a given application in mind? I think that's one of the interesting questions that we can explore as part of a future research. In order to do that, we will need to collectively think about how we design machine learning models, system optimization, and how we design together and bring machine learning as one of the first-class citizens in this part of research. Another interesting topic that I think is emerging is thinking more broadly about this life cycle of learning intelligent applications. So traditionally, when you think about intelligent applications, usually you collect data set, you build a learning system, and you train a model for it, and then you deploy it. On the other hand, actually, the learning system is actually more interactive, right? For example, when you are building a self-driving car system, usually the learning system will need to interact with the environment, and we will need to tackle cases where new data, new models, and new tasks coming in. And the question is, how can we build a learning system that is sustainable in that scenario? So there are quite a few challenges that we can tackle. For example, how can we do effectively transition of the model as we grow the model complexity? How do we acquire data? And more importantly, I think it's important to be able to build real-world learning systems as testbed to test out the idea. In this case, I do think that TVM and other systems is an interesting example where we have continuously getting interesting new machine learning workloads, and we can use that as a testbed to test a lot of ideas on how do we continuously evolving a learning-based system. So to summarize my talk, in the beginning of my talk, I talk about a few elements of the machine learning system that we learned about during our past research, including it's important to build a learning system that are accessible and build scalable solutions so that we allow users to be able to make use of the computing power that are available. Through TVM, we find that it's really important to build intelligent solution to automate a lot of the machine learning system itself. And it's also important to build something that's full stack that considers the high-level abstraction, the program system interface, as well as the hardware architecture. And finally, it's also important to consider a lifelong evolution cycle of the learning system, so that to build a system that can sustainably sustainably execute in the future and be able to improve by yourselves. So with that, I would like to conclude my talk and be more than happy to take any questions. Thank you.
Great. Thank you, Tianqi, for the awesome talk. Let's give you a round of applause. In the virtual world, we do that with this icon on Zoom. Let's see if the audience can find the icon. Yep. Thank you. Very educational deep dive on these systems. Any questions from the audience? Raise your hand if you have questions and unmute yourself. No, they're still digesting. While they are digesting, I have another question for you, Tianqi, about where you see this landscape going, especially in terms of the access patterns of these operators that people are building into these models. In particular, two things, sparse models like sparse neural nets, and the second one is graph nets and graph convolution and stuff like that, where the access patterns have become really funky. What do you think about this landscape of these optimizing compilers? How can they adapt to that? How can the hardware adapt to that?
Yeah, I think these are both excellent questions, right? I think, in both cases, I do think compilers do have a play to have a say in there. For example, in terms of sparse computation, there are works like MIT's Taco on optimizing sparse tensor computation. And there are also works particularly using TVM to optimize for graph neural networks. So I don't know if that paper is published, but in this December, we have a incoming developer conference called TVM Conference. If you Google tvmconf.org, you will be able to find a preliminary agenda there. And there will be talks about how we can make use of a compilation to optimize for graph neural network computation. Sparsity is definitely another interesting theme in here, right? So in this case, sparsity is a way for us to get lower compute to memory access ratio, and we have some preliminary results. For example, at OctoML, we had a blog post showing that by using TVM to smartly optimize for sparse computations, you can get 2x to 3x cost reduction in terms of like a BERT inference on the cloud. So both of the areas are definitely interesting areas for machine learning compilation to go and optimize for. I would say there are still a lot of open questions there in a sense that, what are the best models that fit into those optimizations, as well as how can we design good optimization primitives that really covers all the potential optimization that are available in this case. Yep.
Got it. Okay. Audience questions? Anyone? I still have a couple of questions, but I want to give the audience a chance. Yes, Tara, go for it.
Oh, hi. Mike, I had a quick question. When you were explaining TVM, I didn't quite follow how the ML cost model is trained. I was wondering if you could explain that again.
Yeah, so the idea is that we, for given program configurations, we can send those program configurations to a target hardware. So you'll be able to get a label data in that sense. However, we don't want to do that for every program because there are so many of them. So what we can do is we can use this collection process to collect training data while still build a cost model based on the input configuration. So we'll featureize the input program based on the access patterns and then use that to build a cost predictor. And then the cost predictor can then be used to drive to find more promising regions in the search as opposed to doing a search randomly.
Okay.
Yeah.
Thank you.
More questions from the audience? We still have some time. I do have two long-term questions for you, Tianqi.
Okay.
Pick your brain on that. One, a little birdie told me that Facebook and Google are working on their own new programming language for differentiable programming.
Okay.
What is your take on that? How will that disrupt this landscape of ML compilers and architectures and so on? And what do you think is the implication for productivity of deep learning users?
Yeah, I think that in terms of differentiable programming, the idea is that, it's more like it generalizes what deep learning framework can do, right? As I said, deep learning framework is already doing differentiable programming, yes. But potentially differentiable programming gives you more certain capabilities, right? And that means that there are a lot more things to optimize for. Besides sometimes it could be possible that they might go beyond the tensor computation. And so for tensor compiler themselves, I think there are two implications. First of all, it might means that, the input specification need to be more generalized, right? You want to be able to handle the programs that the differentiable programmer, differential programming language might be able to give you.
Mm-hmm.
Another implication is that, maybe you also want to bake some of the automatic differentiation into the intermediate representations that we have in the compiler, so that it also gives us the ability to be able to differentiate through, right, the optimizations, and when necessary provide gradient to the high level system.
Right. Okay. So you think there's going to be a lot more scope of work in this space once that sort of system comes around, because it's going to be even more complex.
Exactly.
Okay, cool. Questions from the audience? More people, feel free to raise your hand. Oh, okay.
Maybe just
Ying,
this is Ying. Maybe just like a dumb question. I'm new to this space. Just wondering how many new types of like operators are you seeing, and how many new types of hardware are trying to run machine learning models?
Yeah, that's an excellent question. So in terms of operators, it's not necessarily a new type, because in a lot of cases, when you are, if you look into NVIDIA's library for convolution, you can find basically it's the if there else cases of a lot of special cases. In the sense that for different input shape, you might want to pick a different implementation strategy. So even for convolution, 2D convolution alone, for different workloads, you might have, like they are considered as like a different quote-unquote operators from the optimization point of view. And besides that, there are also new emerging operators like 2D, 3D convolutions, matrix multiplication, and if we multiply that by the potential input shape configurations, that's a huge space. And in terms of hardware backends that are emerging, right now a lot of cases we see a lot of use cases in both traditional space like mobile CPUs, GPUs, as well as microcontrollers, where there are a lot more variations. Like if you are looking at Cortex-M class, new RISC-V, like CPUs, there are quite a lot of new variations. And in terms of machine learning accelerator, it's hard to comment on how many accelerators are emerging, but at least given the amount of startups that are emerging, all of them will need a software stack. So that my guess is that eventually all of them will need some solution like TVM to be able to automatically handle a lot of the heavy lifting pace, or alternatively they can build a huge team of engineers to go and support the big spectrum of operators that people are interested in. Yeah. And for reference, the number of operators that we have in TensorFlow is around, I think, at 1,000 level. So right now.
Oh, interesting. And another question is like, so TVM is for training, right? So what would you change if you want to use this for inference?
Oh, actually, to clarify, so TVM, most of the optimization is built for inference, not training.
Oh, okay.
In our previous experiment, but we are also working on optimizing for training workloads. So we do train machine learning models to predict the cost and generate programs for both training and inference in this perspective. Yeah.
Okay, thank you.
Okay, thanks, Ying. I was going to ask a follow-up to that too. So training, NVIDIA has a monopoly now with GPUs and stuff. And where do you think the landscape is going to go there? Is NVIDIA going to remain the king? Do you see emerging hardware accelerators and compiler stacks dethroning 2DNN and GPUs in the near future from Google or someone else?
I think, in this case, right, Google is doing a reasonable job, except that TPU is, the accelerated TPU stack is still only closed source in Google. NVIDIA still have a huge advantage in terms of software stack they have, right? So the ability to be able to keep up with this software stack is really amazing. And the CUDA programming model really builds a huge community behind that. So I don't think that's going to change in a near-term future, but we do want to disrupt that in terms of, I think having a more generic compiler solution is a way to try to disrupt the potential landscape in training, right? The idea is that, if in a lot of cases, we do not have to necessarily, build a solution that's specific to CUDA, but build operators, say on top of TVM or some generic solution that allows you to optionally still target NVIDIA, but also directly retarget to other devices, then we'll have a much better landscape where we will be able to switch across hardware devices more easily. But that is still something that need to be worked on. And my guess is that this can happen in a few years, but it will need collective effort from the community.
Okay. Should be fun to watch. Who knows?
Mm-hmm.
These architecture companies change over the course of a couple of decades. They're not like software companies.
Exactly.
Last thing is another trend I'm seeing in the cloud services. I don't know if you're following the data system space, like database space is being severely disrupted by cloud native architectures and virtualization at all stacks and disaggregation and so on. And of course, we have Yi, who's an expert on that. GPUs, people are building virtualization layers, right? So now you can share the GPU for different users and different execution models. I would assume that would generalize to machine learning workloads. And how do you see the future of compilers like TVM in that space, where the underlying hardware is no longer fixed, but
exactly. I think that's also a very exciting question, right? In a sense that traditionally, when you hire a bunch of engineers to go and optimize for a GPU, NVIDIA is only releasing one GPU every year, or like a few variants of that one GPU every year. So you can still afford to build libraries every year for that GPU. But now you have virtualization layers on top. So different execution environment will might mean that you need completely different code for that execution environment. And I do believe that will bring new challenges for machine compiler, like how can you quickly adapt to the different environment, but also brings new opportunities in the sense that that's really a case where you can no longer rely on libraries, unless the library is really generic, which I believe is a really hard case to build. So yeah.
Interesting, because I was at this Strata Data Summit last year, and there was a company that was building microservices on top of AWS Lambda, where they want to push the latencies and they want to sell at the level of milliseconds. And inference is the workload for serverless, right? That's one of the killer workloads. And so there, with these sorts of levels of virtualization, I was just wondering, how is the compiler stack going to look in the future now with these sorts of elastic inference infrastructure? Okay.
Yeah, I think that's definitely a very interesting topic in the sense that, in an environment like serverless or cloud native, right? It means that the amount of runtime environment, like traditionally when you build compiler, you only need to think about hardware target. But now you want to think about both hardware target and runtime environment. And that's a much bigger spectrum than the hardware backend alone.
Got it. Okay. Great. Any other questions from the audience? You're at the top of the hour. Feel free to raise your hand. More questions about any of the thing that Tianqi has worked on. He has so many awesome stuff that he has worked on XGBoost, MXNet, TVM. It's pretty remarkable. XGBoost, if the audience doesn't know, it's like has become the de facto standard for Kaggle contests and a lot of learning tasks on tabular data. Okay, so if not, let's thank Tianqi again. I hope I pronounced your name right. It's Tianqi, right?
Yes.
Okay, great. Thank you for joining, Tianqi. And thank you to the audience for joining the database seminar.